When you are dealing with really large datasets, bulk ingestion in Qdrant can actually trigger resource saturation failures. These are pretty different from your typical request-response issues. Now picture this, a production incident we had. We tried to ingest over 5 million technical manuals, that's more than 10 million vectors, into Qdrant. This scenario really highlights something. Bulk ingestion fundamentally shifts how the system behaves. It goes from a standard request-response pattern to something dominated by resource saturation. We are going to dive into two critical failure modes. First, segment merge contention, and second, memory exhaustion, often called out-of-memory or errors. Understanding these failure modes is absolutely vital for building robust RAG infrastructure, especially in high-stakes domains where reliability is paramount. Bulk ingestion stresses systems differently than normal requests, so the key idea here is that large-scale data loading presents unique challenges beyond just typical API interactions. Mainly, it is related to resource limits.
Okay, so let's dive into a specific event. This really highlights some issues. We are talking about a large-scale backfill, millions of technical documents, specifically 5 million. The goal was to get this done in 36 hours using a 3-node Qdrant cluster. Each node had plenty of power, 16 cores and 64 gigs of RAM. At first, things looked good. The ingestion was performing well. We were seeing about 2,000 vectors per second. Pretty solid, right? But then something happened. After ingesting around 2.4 million documents, the system's performance just tanked. It degraded dramatically. Throughput dropped way down to about 50 vectors per second. Yeah, only 50. What was supposed to take maybe 12 hours turned into an estimate of several weeks. This put important project deadlines in jeopardy. This sharp drop in performance is what we need to figure out. A backfill of millions of documents failed dramatically. So the main takeaway here? A huge data ingestion task hit a wall. Performance degraded severely, and it completely missed its deadline.
So how do we figure out what went wrong? We need to look at the forensic signals. These are the patterns in our telemetry data. Now, there's a big difference between two types of drops. You see, one is gradual. We call that a slope. The other is sudden, a catastrophic drop. That is a cliff. A slope usually means resource contention. Background stuff is struggling to keep up with the ingestion rate. A cliff, though, that typically means a crash. Often, the system's out-of-memory killer did it in. By looking at the shape of the throughput degradation, we can start to guess what is really going on. Some key things to watch are the pending operations count and the ratio of index to total vectors. Throughput slope or cliff reveals the failure type. So the main idea? Analyzing the shape of that throughput drop, whether it is gradual or sudden, helps us diagnose the root cause of ingestion failures.
Okay, let's talk about the first failure. It is called segment merge contention. Now, in Qdrant, data comes in. It is written into these small temporary segments. And then, periodically, there is this optimization process. It merges those smaller segments into bigger ones, more efficient ones. Contention happens when you are ingesting data way faster than the optimizer can keep up. And that, you see, leads to an explosion in the number of segments. In our incident, the segment count just shot up from about 280 segments to over 1,400. And a high segment count, well, it makes every single operation much heavier. It increases the overhead. So performance just starts to degrade, gradually. Here's how you spot this mode. You will see a gradual decline in throughput. We call it a slope decline. There will be high CPU usage because the system is busy merging. The segment count will be climbing fast. But here is the crucial part. Memory usage stays stable. The Qdrant process itself, it is usually still healthy. Too many segments choke performance gradually. So the main takeaway, segment merge contention. It happens when ingestion is faster than optimization. It causes that gradual performance drop, and you can spot it by that slope decline and high CPU.
Okay, so let's talk about another big failure mode. This one is called memory exhaustion. You might know it as an out-of-memory error, or an error for short. Vector databases, you see, they just love memory. They need a lot of it. Think about things like the HNSW graph and storing your document data. It all adds up. Now, when you are ingesting a lot of data, your RAM usage can really shoot up. That is because of building the HNSW and indexing your documents. Plus, there are internal batching things. So here's the thing. If all this memory use goes beyond what your node actually has, the operating system has this thing, the killer, and it just shuts down the Qdrant process just to get that memory back. How do you spot this? Well, you'll usually see throughput drop like a sharp cliff, and memory usage might look like a sawtooth, or it just keeps climbing. And you'll see messages in your logs. You'll notice nodes restarting a lot, or they'll be marked as killed. The segment count might not be that high, or it stays pretty steady. Exceeding RAM limits triggers the killer. So the main takeaway here is this. When you run out of memory, your process crashes. You'll see that cliff drop and those logs. It's different from that merge contention we talked about.
Okay, so let's talk about handling bulk ingestion. It can get tricky. To really get it right and make it as fast as possible, we need to look at how things can go wrong and then what we can do about it. First off, if your throughput is low, don't jump straight into Qdrant's guts. You might just have a network problem. Always check that first. Here's a big optimization. For really big data loads, you can actually turn off indexing. Just set that indexing threshold to 0. This lets you just dump the raw data in way faster. Then, once all the data is loaded, you can turn indexing back on. It builds the HNSW index all at once. It is a much cleaner process. Here is something super important to watch. Keep an eye on the difference between total vectors and indexed vectors. If that gap keeps getting bigger, that is a sign indexing is having trouble, or maybe it is failing. Disable indexing for faster bulk loads, then re-enable. So the main point here is this. Smart configuration, like turning off indexing initially, and paying close attention to what is happening, that is what you need to stop ingestion failures and fix them if they pop up.